Hello everybody, welcome to Guidancee Education channel. We will see the topic that is discussed in this video. We are continuing class 11 physics, thermodynamics. The topic discussed is Carnot engine, part 1. Under this, we will discuss features and essential parts, working and processes taking place, PV diagram, how to draw the PV diagram and its explanation. This topic is of great importance, so watch the video completely without skipping so that you can understand all points clearly. And if you think the video is useful, do like the video, share the video with your friends who may also be benefited, and also leave your feedbacks as comments in the comment box below. If you're watching without subscribing my channel, do subscribe it now and support me. And also press the bell button and all button for notification of more videos like this. Thank you very much. Come, let us discuss the topic. Our topic is Carnot engine. As soon as you hear this term, a number of questions will automatically arise in your mind. Like, why this is called Carnot engine? What type of engine is this? Where exactly is this used? What are the essential elements, that is essential parts of this engine? How does this work and what is its benefit? You have to answer all these questions. But before we answer these questions, please watch the video completely without skipping so that you understand all points clear. And if you have not yet subscribed my channel, do subscribe it now and also press the bell button and all button so that you get intimated as soon as new videos are posted. Definitely like my video and also share it with your friends who may also be benefited. Leave your feedbacks as comments in the comment box below. Okay, let us see the topic. We have already seen that the greatest concern in thermodynamics is the efficiency of the heat engine, which is always less than 1, that is less than 100%. A lot of heat is wasted here. Why heat is wasted? This is because we know the heat engine which we use commonly is an irreversible engine. Irreversible processes we know are associated with dissipative forces, which is the reason for wastage of energy. I have already posted a video on reversible and irreversible processes. If you have not yet watched that video, click the I button in order to watch that so that these points will be very clear for you. As back as 1824, Nicolas Sadi Carnot designed an engine which was named after him as Carnot engine. The special feature of this engine is that it is a reversible engine. That is, the working substance passes through several states or stages and finally returns to the initial state. Since the process is reversible, there are no dissipative forces, so energy is not lost. Therefore, efficiency is more than 1, that is more than 100%. So that is the benefit of Carnot engine. But it is an ideal engine. That is, it does not exist in reality. It cannot be fitted anywhere. It is a hypothetical engine. It is not a real engine. We will see the parts of the engine. It has a source which is at very high temperature. Let us mark it as T1K. This surface is conducting. The second part is the sink at a very low temperature. Let us mark it as T2K. That means T1 is greater than T2. I will represent the sink. This end is conducting. The third part is a cylinder with non-conducting sides and conducting base fitted with a non-conducting and frictionless piston. So all dissipative forces are avoided. The side walls are shown thick. The piston base also is shown thick. Only the base of the cylinder is shown thin. It is conducting. The fourth part is the working substance, which is an ideal gas. It fills this cylinder. Ideal gas is a hypothetical gas. It does not exist in reality. And there is a non-conducting stand. Working of Carnot engine. The Carnot engine works between two temperatures, T1 and T2. For convenience, the working is split into 4 steps. Step 1. The initial state is P1, V1, T1. That is, the working substance, which is the ideal gas, is in the initial state P1, V1, T1. The cylinder and the working substance now rest on the source, which is at high temperature T1K. The bottom portion of the cylinder, which is conducting, now rests on the source of heat. The upper surface of the source of heat also is conducting. The working substance absorbs heat from the source, and the temperature of the working substance and the source become the same. Since the source is at very high temperature, a small amount of heat absorbed by the working substance does not change its temperature. So the temperature remains constant. As heat has been absorbed by the ideal gas, what happens to it? It expands and pushes the piston doing external work. So during step 1, temperature remains constant and expansion work is done. The system changes its state to the next state, that is P2, V2, but T1. We have already stated that the temperature is constant. So the process taking place during step 1 is isothermal expansion. So we will pass on to the next step, that is second step, step 2. What is the initial state? The initial state of step 2 is the final state of step 1. It is P2, V2, T1. Now the system is moved and it rests on the non-conducting stand. So using the heat present inside the system, that is using the internal energy, the gas expands further. That is, external work is done by the system, and the state of the system now changes to P3, V3, T2. So all the state functions have changed. The process that takes place here is adiabatic expansion. In the first step, isothermal work is done. In the second step, adiabatic work is done. Now we will see step 3. The initial state of the system is P3, V3, T2. That is the final state of step 2. The system is now placed on the sink. Since the bottom surface of the cylinder is conducting, some amount of heat is transferred to the sink, and the temperature of the sink and the cylinder become the same. The temperature of the sink is very low. So even if it gains some heat, the heat remains the same. We have already seen that T2 is less than T1. So the system has now attained a lower temperature. When the system loses heat, the gas undergoes compression and the piston moves down. That is, compression work is done. Work is done on the system, but the temperature remains constant and the state functions change to P4, V4, T2. So the process taking place during step 3 is isothermal compression. That is, the system does isothermal compression work. Now, the last step, that is step 4. The initial state is P4, V4, T2. That is, the final state of step 3. During the fourth step, the system again rests on the non-conducting stand. The ideal gas undergoes further compression and the state of the system returns to the original state, which was P1, V1, T1. I hope you remember when the cycle started, the initial state was P1, V1, T1. You will notice that in step 4, all the state variables, that is P4, V4, T2, has changed to P1, V1, T1. So the whole process has reversed. So this is a cyclic process. All these 4 steps together constitute the Carnot cycle. During the last step, adiabatic compression work takes place. Let us see the PV diagram for Carnot cycle. But before that, we will see the steps in Carnot cycle. Step 1, isothermal expansion. Step 2, adiabatic expansion. Step 3, isothermal compression. Step 4, adiabatic compression. The PV diagram for Carnot cycle should include the graphical representation for all these steps. This is the X and Y axis with pressure represented along the Y axis and volume represented along the X axis. This is origin. Step 1, isothermal expansion. The graphical representation is like this. This is the initial and this is the final point for step 1. The initial point is marked A. The state of the system is P1, V1, T1. The final point of step 1 is B. At initial point A, pressure is P1 and volume is V1. At the end of step 1, that is at point B, pressure decreases to P2 and volume increases to V2. Temperature remains constant because the step is isothermal expansion. I will mark P2 and then V2. Step 2, adiabatic expansion. This is the graphical representation, and for adiabatic expansion, we know the graph will be steeper. B is the initial point for step 2 and the state function is at P2, V2, T1. C is the final point of step 2. At point C, pressure decreases to P3, volume increases to V3 and temperature changes to T2. Let us mark P3 and V3. Temperature is T2. The third step is isothermal compression. Please note the direction of the graphical representation. D is the final point of step 3. Volume decreases to V4. Pressure increases to P4. Temperature remains constant at T2. Let us mark P4 and V4. Initial volume is V3 and the final volume is V4. We are moving from right to left along the x-axis, so the volume is decreasing. In the y-axis, we are moving in the direction of the increasing order, so pressure increases to P4. Temperature remains constant, so it is isothermal compression. Volume has decreased. Now the final step, step 4, adiabatic compression. Note the direction of the graph. The system returns to point A. The state returns to P1, V1 and T1. So the system has completed one cycle. So when one cycle is completed, the system returns to its initial state. During each step, some amount of work is done. The total work done is the area included by the loop A, B, C, D, A. I hope it is clear. We have to derive an expression for calculating the work done in the Carnot cycle and also discuss the efficiency of Carnot cycle. That we will do in the coming videos. Otherwise, this video will be too long. I hope this video was of great use to you. If you think it is useful, do like the video, share the video with your friends and also leave your feedbacks as comments in the comment box below. If you are watching without subscribing my channel, do subscribe it now and also press the bell button and all button so that you get intimated as soon as new videos are posted. Thank you very much. Bye for the present. Take care.